We have an exciting afternoon here. We have Parness from JPL. If you don't know him, or hopefully you all know a little bit about him, he's done some really amazing work with climbing robots in recent years, and but he's got a great history of work at MIT and in Stanford, and I actually don't know how long you've been at JPL. But
9.5 years, yeah.
We're commiserating over writing flight proposals.
Yeah.
And as maybe you noticed here, there's a new title. So this is actually Aaron's farewell talk. He's finished up at JPL and headed to Amazon. So doing well on that. But should be great. So thank you. And, take it away.
Great. Yeah, thanks everyone for coming out. I'm really excited to be here. So at JPL, I worked mainly on robotic mobility systems and grippers. That's what the talk will be about. But I am excited. I'm going to be out at Amazon starting in about a week and a half, working with Sid Srinivasa, who I think many in the CMU community probably know, and working on manipulation tasks there as well for the fulfillment centers. And so if you have interest in either of these companies, both of them are recruiting and hiring, reach out to me. OK, so let's motivate the research a little bit. It's about roving. These are the rovers that we've flown. So you see the Soviets' Lunokhod up there, the one that the astronauts got to drive during Apollo, our Mars rovers down here on the bottom. Rovers gives you this immense advantage over just a static lander. You can access terrains that are far from your landing zone. You can look at gradients in different scientific factors. You can land somewhere safe and then rove somewhere dangerous. But you'll notice one thing that's similar between all of these is that they're wheeled. They're limited to about 10-degree slopes. Unfortunately, this is kind of the unlucky coincidence of our solar system. A lot of the science targets that we want to investigate are not on flat slopes. So this is a picture that the Opportunity rover took of a crater outcrop. The scientists were extremely excited because if you look in detail, maybe hard to see here, there's stratigraphy. So this was the first evidence of sedimentary rocks on Mars. Gave some indication that it used to be wet, liquid water. That's how sedimentary rocks form. We spent about 3 months trying to drive the rover up to this outcrop unsuccessfully. It just wasn't safe, and so we had to move on. Another example of this is a picture that the Curiosity rover took. Again, you see that layering. It's the same thing. If you wanted to learn about the history of Arizona at the Grand Canyon, you would want to be in those canyon walls, kind of going back in time as you went lower and deeper into the canyon. We want to do that study on Mars, and the current rovers don't allow us to do it. There are these other features, very interesting. These are seasonal. I hope you can see the kind of dark spots here. These appear in the spring and disappear in the fall. There's some kind of liquid water. We think they're briny, salty water. They're on very steep slopes on certain crater walls on Mars. Again, can't get there. There's also caves. We see the entrances to thousands of caves in the volcanic regions of Mars. And it's not just Mars. So this is a picture of Enceladus. It's a moon out at Saturn. There are active geysers spewing out material from a saltwater ocean beneath its icy crust. These are the best pictures we have of the surface, about 6 meters per pixel. You can tell it's not flat, benign terrain that you want to drive across with the Curiosity rover. You also see pictures of Europa here. This is what they call the chaos terrain. It's where the ice crust is getting overturned. Europa is a moon out at Jupiter. Very interesting, again, because it has a liquid water ocean and a lot of complex organic chemistry going on. The fun doesn't stop. This is a picture of a comet. This is a 67P CG. It was taken by a European spacecraft called Rosetta. Comets bring a new wrinkle in that they're in a microgravity environment. So, milli-G levels of gravity. So you really can't drive because you have no pressure on your wheels. You may just hurtle yourself out into space. If you've seen pictures, this comet kind of looks like a rubber ducky, and at the neck, super interesting, there's this big crack. Is that a fault that indicates maybe this comet is breaking apart? We don't know. We can't get there, right? So, OK, I think that's enough examples, but there are a lot more. In today's paradigm, we sort of have a 2D grid. We identify obstacles. We drive around those obstacles. That's how we operate the rovers on Mars. And so our work is really motivated by trying to get to the third dimension, trying to climb on terrain where the obstacle is your intended target. The good news is that there may be one coming in the near future. This is a mission concept called Moondiver. I spent the last 2 years leading this mission. It's in competition with about 20 other concepts right now at NASA headquarters. We'll find out in February. Its target is this. This is a cave on the moon. It's called Tranquillitatis Pit. As much as we've studied the moon, we didn't know it had these giant holes in it until 2009. So this was a picture taken by LROC in 2010. It's 100 meters in diameter and more than 100 meters deep. And there's a couple of them sprinkled around. This one is between the Apollo 11 and Apollo 17 landing sites. And it has, again, some of this layering, which the scientists are extremely excited about to tell you about the history of volcanism on the moon. So if you look up at the moon, there's the dark patches. That's the mare. That's the volcanic terrain. Did that all come out at once? Did it come out episodically over a long period of time? That's important because it tells us kind of about how planets form, broadly speaking. The moon is a good example of something that's sort of easy to understand. So here's the way we're going to access that. We land very close to the edge of the pit, and then we rappel down using the lander as our anchor. So this is a rover called Axel. It was developed primarily by a researcher named Isa Nesnes at JPL. Our principal investigator for the mission, though, who's a scientist, is Laura Kerber. And she uses a great line. She says, we go to the moon this time not because it is hard, but because it is easy to interpret. So hopefully this will launch in 2025 or so, which in terms of an aerospace project life cycle is actually very near term. Again, we'll get the go-ahead from NASA in February if this happens or not. This is the other side of that baseball card that we submit. Okay, so beyond that, if you don't just want to drop yourself down on a rope, if you want to climb up from the bottom, if you want to go sideways, if you want to have precision in where you're putting your instruments, you may need a climbing robot, and that's a lot of the research that's been happening in my lab. So I'll talk to you about rock climbing first. So this is the lemur rock climbing robot. There are two kind of main takeaways that if you don't remember anything else from the talk, besides some pretty pictures of planets and robots, I hope you remember that the philosophy that's guided all of this work has been based on iterative design and testing those designs in the field. So we go out to the extreme environments on Earth to really understand how our system performs and how we need to fix it before we can send it out to Mars or the moon or comets where there's really no opportunity to fix it. So as an example of this, this is the 3rd generation of the robot, 4th, maybe 5th generation of the grippers, and it's actually the 3rd time we're in this cave system. This is a cave in New Mexico. So New Mexico's on the right, Mars is on the left. It's like one of those pictures that if you were faking it, this would be too close. You would have to make it look a little different. Scale bars are different. So it's interesting that lava tube size seems to correlate inversely with gravity. So lava tubes are bigger on Mars, and they're absolutely gigantic on the moon. Okay, so how do we explore these lava tubes? We use a technology called microspines. And this goes back all the way to when I was a grad student at Stanford. Mark Kutkoski's lab developed the first versions of these, along with some other grad students, Alan Asbeck and Songbei Kim. It's essentially a sharp hook on a compliant suspension structure. So it's opportunistic. We're not trying to predict where the rough spots are going to be. We just put the hooks down and drag them across the surface. And it's also probabilistic. So if we get about 10% of the hooks to catch, we can support the loads of the robot. You can see different versions of them here, different flexure designs. This is essentially how it works, though, all of them. So you drag along the surface, the hook catches, you see that accordion flexure stretch out. That means it's bearing load. In this case, 1 to 2 newtons is sort of the max capacity. So you really need to have good load sharing for a robot that weighs 20 kilograms if you're going to be able to climb up the wall. Okay, so let me see. I'm actually going to skip ahead and come back to this one, I think. This is what happens when you have the USB version of your presentation. So microspine scale. This is a video of a show I did for the Discovery Channel. I took about a month off in grad school, and I built 3,000 microspines times 2 for these 2 tennis racket kind of paddles that allowed a person to climb up the outside of a parking garage. This is in downtown Oakland. She's a professional rock climber. It was on a show called Prototype This. It was on the Discovery Channel. It was so good that they canceled it after 1 season. But this was pretty awesome. You can tell I'm excited and young and full of energy in this video. So microspines scale, right? Even though each one of those hooks is only supporting 1 or 2 newtons, if you use enough of them, you can get a whole person up. Let's see. So we were here. Climbing a rocky cliff face is a different problem, though. So a parking garage wall is rough, but it's kind of predictably rough. If you want to climb a cliff face, you're dealing with a natural terrain that tends to have fractal roughness. So it's rough at all different length scales. And so one of the tricks we did, one of my first projects here at JPL, was to generate a hierarchical compliance. So not just the microspines, but a gripper that would also adapt to the terrain it was on. So the microspines themselves, pretty good at the millimeter scale. But we would package them into fingers or cassettes of 10 to 20 microspines that could conform to surfaces and load share at the centimeter scale. And then you need your robot arm and your gripper to kind of match the terrain and be placed in a reasonably good configuration at the 10 centimeter scale. So you can see this in action. Here we have microspines that have extended. That means they're bearing load. So again, 30% maybe in this is a very good grip. We only need about 10%. Here you can see those fingers. They're at different angles, at different distances away from the center. This is all done passively. And here you see both of those 2 actions superimposed on one another. And you know, it sort of worked on rough rocks. And the good news is most of the rocks in the solar system are really rough. If you find a rock that's like a bowling ball, it's probably because it's been processed by liquid water tumbling down a stream or moving through a glacier. And that would be a much bigger deal than if our robot fell off if we found such a rock on Mars or on the moon. So this was 2012 or so, and I can tell by my shoes, which have gone out of style since then. Maybe we're never in style. I want to talk a little bit about the mechanism, though, as well. So it's a highly under-actuated system. This gripper has 250 sharp hooks. It's controlled by 2 mechanisms. So one lifts all of those fingers, all of those cassettes, up and away from the surface. There are torsion springs that bias them into the surface so you can grip upside down or in microgravity. And a second mechanism pulls them all in towards the center. Those 2 actions always happen in the same sequence, so you can actually stack them on the same lead screw if you want. We get asked a lot, does it work on dirt or if there's dust on the surface? And the answer is absolutely. So this is a gripper former CMU or recently graduated CMU PhD built while he was an intern in our lab, Nitish That. That shows, yea, verily, we can pull rocks out even if they're covered in dust. Some of the technologies I'll show you later, not so good with the dust, but microspines just cut right through. And if you're on a vertical surface, you don't really expect to have more than a few layers of dust, right? You're not going to find 6 inches of dust hanging on a vertical cliff face. Okay, so we also got to test this on NASA's Vomit Comet. Highly recommend doing that if you ever have a chance. So this was to prepare for an asteroid mission. So on an asteroid, if you were going to try and drill a sample in a rock, you have a problem. You have to react those forces and torques. When I talk to my wife's kindergarten class, I tell them if you had your drill from the garage and you squeeze the trigger, you're going to spin around the drill rather than the drill bit spinning in the borehole. Employ the microspine gripper, react those forces and torques, and we can drill in 0G. I love this video also because you see that cloud of debris kind of shift partway through. The pilots are actually making slight corrections as you're in your sort of 20 to 30 seconds of free fall to try and keep you at 0G. So you're actually in this kind of minus 0.02 to 0.02 G. And John King here in the front was also a student with us, got to come with us during one of his internships as we tested this and built the air-bearing Stewart platform there that prevented the gripper from slamming into the floor of the airplane when we went into the double gravity mode coming out of the parabola. All right, so that was supposed to be earlier. There we go. So here's what the mechanism looks like. It's, again, a lead screw. It's pulling a center plate up. And it's got a bunch of extension springs that are providing the compliance and the load sharing at that centimeter scale at the cassette level. And then the flexures in the microspines themselves are doing the load sharing within a given cassette. So 250 hooks, 2 degrees of freedom. Here you can get a sense of the design iteration. So we moved from rapid prototype, a lot of 3D printed parts, off-the-shelf servos, to a design that was more flight-like, built with flight-like materials and processes. We upgraded some electronics there and created a mount so it could be tested with an industrial robot arm, and then went to a fully form, fit, and function prototype. This wasn't able to be put in a thermal vacuum chamber. We didn't have all the right greases and other things like that, but it was otherwise exactly as the gripper we would have flown to an asteroid. So this was for a mission to try and push an asteroid out of the way if it was happening to come towards the Earth. So we were going to practice on one that wasn't going to hit the Earth. You'd hate to be the guy that pushed it into the Earth instead of away from the Earth. So a fairly large gripper was going to pull a school bus-sized boulder off of the surface of that asteroid, hover around one of the poles, and use a gravity tractor. Essentially, the gravity between the spacecraft and the boulder over the course of about 6 months would have tugged the orbit of that asteroid enough that it would be a near miss instead of a hit. So as part of that tool, we had not only the gripper, but a drill down the center, similar to the prototype I showed you previously. We made a design decision early on to use a pretty complex transmission to power that drill. So the robot arms had 3 actuators, three torque transmissions at the end of the arm. And rather than flying electronics in our gripper and dealing with the thermal consequences of having electronics out in our gripper, we decided we would use those motor outputs from the robotic arm to power our gripper. Now the problem was we had 7 mechanisms now between the 2 in the gripper, a spindle, a percussion, a chuck, and a feed on the drill. And we only had 3 outputs. So we had a 2-state clutch since you were never drilling and gripping at the same time. So that's why all these gears are in here. If there's any mechanical engineers in the room, I was mechanical. This was like super fun. Here's what it looks like on the underside. We used a lot of Sprag clutches, which are similar to the bearings in the back wheel of most bicycles. So essentially, if you would spin one drive clockwise, it would be the spindle. Spin it counterclockwise, and it would undo the chuck. This is what it was driving. Here's that rotary percussive drill. So since we were drilling in rock, we use a masonry type drill, one that hammers as well as spins the drill bit. And then here's the gripper. I'm not sure, Andrew Willig's in the back there, another CMU guy, did a lot of the work developing this gripper. It's got this flying bridge that again houses all of those springs to distribute the forces to the different cassettes of microspines. And then it's got this linkage that I'll talk about in just a moment. And this cam mechanism here is what pulls those up and away. So those are the 2 degrees of freedom we talked about before. So that's what it looks like, except this guy's on the wrong side. And then you'll have to pardon I think this is a Mac versus PC PowerPoint issue here. But this is the linkage mechanism. So we went away from these prismatic joints at the end of the gripper, which was just a polished dowel pin inside a journal bearing, and instead went to this linkage mechanism because we were getting unwanted collisions with the gripper and the rock. So essentially, we'd come down on the rock, but it wasn't the hooks that were making contact. It was like the elbow or the wrist of that mechanism. And really what you want is the hooks. And the hooks in this case would be mounted out here, some passive compliance in the roll joint out there. So another piece of a bicycle, we use Bowden cables to route the motion down to each one of these fingers. And this solved quite a lot of that problem. We also matured the microspines quite a lot. So I showed you early on some of those varieties. Here's a lot more. So the labels here are some of the inventors of the different varieties. HS is a professor at Ohio State, Haijun Su. SL is another CMU alum who was here in the beginning and then left, Sherman Lamb. EZ is a guy from the BYU Compliant Mechanisms Lab, Ezekiel Merriman. And then we really should call V3 AW for Andrew Willig back there, but that's the one that won out in the end. It was challenging. So these flexures, you wanted them to be pretty compliant, but we also had to make thousands of them. And so we wanted to use a mass manufacturing process like a water jet. But this was really right at the limit of what a water jet could produce. So we actually flew Andrew up to Seattle, and he went and saw the new Micromax, Omax water jet and figured out that we could precision water jet these with a much smaller kerf. And lo and behold, that gave us a really nice result, and we mass manufactured them. We did have some other hiccups along the way. This is where iteration really helps you out. We noticed we were getting some binding, and so we did some analysis, and it really demonstrated that we didn't have optimal mounting positions. So if you do a fairly simple analysis, you can see that when you put all of your mounts in a row, and then you load them down here, you get this turning moment that causes binding between those two sliding surfaces. So we fixed that in this design, and that analysis says, oh yeah, we should have no binding. Essentially below 1 would be no binding. And we look at the test data and we see that, right? Here it's bound and then it slips. Here we get pretty symmetric performance. Okay. One of my favorite parts about working at JPL is working with the scientists. One of my least favorite parts about working at JPL is working with the scientists. You can't pin them down on anything. So we were going to a C-type asteroid. This is a carbonaceous chondrite. It's called that because there's a lot of carbon and a lot of water. It's not one of these big nickel, metal, iron chunks. It is kind of more sandcastle-y material. They say, oh, the rock may be very weak. They say, well, how weak is weak? And they say, oh, it'll be weak. And I say, well, I'm an engineer. I need to like design my system to some set of requirements. And they say, well, it could be as weak as like 700 kilopascals of compressive strength. So, oh, geez, that's really weak. That's like you could pick up the rock, squeeze it in your hand, and it would explode in your hand, sort of like the stuff on the left. And I said, okay, that's tough, but we'll deal with that. And they said, well, wait. It might be really hard too, you know. And I say, what do you mean? And they say, well, maybe it could be up to 450 megapascals of compressive strength. And I say, you said kilopascals the last time, right? And I say, yeah. So 450 is like harder than any basalt you can find on Earth. It's like gemstone class of hardness here, so of strength. And I said, really, we don't know it any better than that? And they say, no, I think it's somewhere in that range. I said, great. So we had a test campaign to try and envelope the rocks. And it's funny, you know, and I make light of it, but it's also kind of the motivation, right? We go out and explore these places because honestly, we don't know. You know, nobody's ever been on a carbonaceous chondrite asteroid, and so we could be the ones to find out which scientist was right and which scientist owes everybody a pitcher of beer. So here's our test setup. We've got a 6-axis force-torque sensor behind a rock, and we can mount lots of different kinds of rocks to cover all of those parameters. And then we've got 2 axes to represent the motions of that gripper. And we can cycle through all different kinds of design. And so I'll go kind of quickly through this as opposed to getting into the details, but we did a lot of testing. So here you see kind of a typical test. I think it's pretty hard, but you can see shear forces here coming up And then the normal forces here will start to spike once we start pulling off in the normal direction. So here they go up. You get a lot more shear load capacity than you do normal load capacity. It sort of makes sense. And so a typical data set kind of looks like this. It's not the cleanest, best thing, but the other kind of interesting behavior of these microspines is that you get stick-slip. So it's not a sudden failure. You know, one might fail and the others are still caught. Then that one might find a new asperity to grab onto. And so it's kind of hard to predict what's the total grip force going to be if there's 16 fingers that are all kind of doing this kind of thing. And so we developed a bit of a sampling mechanism where we would bin our data and then sample from that and then do some Monte Carlo to try and predict what the full grip strength would be. And then to provide some conservatism on that, we used the 99% or the 3 sigma low number as our benchmark for what our performance was. We did a lot of sort of design of experiments kinds of testing to try and optimize the flexure stiffness. It's a really hard problem to model. We never really closed on a contact model for that fish hook with these different kinds of rock surfaces that would crumble or deform. And so we took an empirical approach where we tested a bunch of different flexure designs. Here you see we're just cutting out the number of parallel leaf springs that are in this flexure. We looked at different hook angles, angle of attack of the different hooks. This was sort of counterintuitive. It turns out this steeper angle, 60 degrees more orthogonal to the surface, actually outperformed everything else. The hooks wear, so this is some work that Matt Martone, who's up here in the front, another CMU guy, did for us, looking at the performance over time. This really indicated that when we flew to the asteroid and we're going to try and save humanity, you want to have fresh, sharp fish hooks. But of course, in the test domain, you can't remake 1,000 microspines every test you want to run. And so we needed to understand the wear performance, even just to understand our own test results. And so here's kind of what that data looked like, looking at different hook sizes. Kind of a fun side story. We've tried all different kinds of sharp, strong, metallic elements. So sailing needles, fish hooks, sewing needles. I even harvested cactus needles at one point and tried to make microspines out of them. Turns out the fishing industry is really good at making things sharp and strong and cheap. We created a worldwide shortage at one point in 900 BL Tiemco size 8 fish hooks. So if in around 2015 you were looking for those and you couldn't find them, I apologize. And then we got smart and went to the manufacturer and ordered them, by the tens of thousands direct instead of in packs of 25. Yeah. We looked at other things as well, though, in terms of the geometry of these hooks. Again, this is an unsolved problem, is how to do contact modeling of these kinds of fingertips with natural terrains. So if someone's looking for a good topic where we could use some help, that's one for sure. Another kind of interesting finding, we thought, hey, more hooks is probably better. More microspines is better. Can we stack them? And there was an unexpected kinematic effect here that when you started loading in the normal direction, because you have a bunch of compliance in your system, you would actually have the effect that the outer hook would create a moment that would lever the inner hook off the rock. So you either needed an active pitch joint down at the wrist of each of those fingers, if I can kind of use that corrupted analogy, or what we did is just get rid of the idea that we could have multiple hooks in a row. So we just had one hook at the end of each of the microspines. We also optimized the elevation springs and the stiffnesses of these things. I'm going to go pretty quickly through this. We also looked at the number of microspines in a cassette. More is better, but it's not a linear kind of thing. So there's a bit of coupling that's happening between adjacent microspines. We really want them to be independent, but it seems that there's some friction or some hogging of the good asperities by the hooks that find it first, maybe. So we looked at going even thinner, and this was creating even more stress on our water jet process, and so we ended up sticking at 1/16 of an inch for our microspines. So here I'm coming back to our eternal fights with the science community about what the right rock was to test on. So we did a whole suite of rocks here, so many that we've got multiple pages of them, and each of them was meant to represent kind of one potential extreme or one potential combination of what we might find on this carbonaceous chondrite. In the world, there is only one meteorite sample from a carbonaceous chondrite, from a C-type asteroid, or a CL-type asteroid. It's called Tagish Lake. It was discovered up in northern Canada. They find a lot of meteorites up there because you just look for the black rocks on the white tundra. So it's not that they fall more often, it's just that they're really easy to find. Same thing in Antarctica. This kind of makes sense. So the reason we don't have many of them is not because they're not common. These C-type asteroids are fairly common, but because they're weak, they tend to just break up and vaporize in the atmosphere. So we have an oversampling of the iron, chromium, nickel asteroid type, and we have a real undersampling of these carbonaceous chondrites. But some of them made it down. And they were bought by a university, and we got so tired of arguing with the scientists, I called that university up, and they said, if you give a talk, you can come test on the meteorite. And I was like, great. And so I flew up there, didn't tell NASA I was taking the microspines across international lines, and just Canada, right? And we tested, and what we found was it was sort of in the middle. So here's that 700 kPa sandcastle kind of stuff. 2 megapascals. Here's where the Tagish Lake meteorite chunks that we were testing were. And here's the really, sort of hard rocks out here at the end. So that gave us some confidence that, we weren't going to pull this school bus off and have just a school bus size bag of sand after we had drilled into it. Now the drilling is an interesting part that we also needed to test for. So we don't just grip, but we have this hammer drill. And so how do you make sure your grip stays in place as you're hammering with your rotary percussive drill? So we added to our test setup this fancy Home Depot masonry drill and just banged on the back of the force torque sensor and the rock here while we were gripping. And of course, you saw a fall off in performance, the yellow here being with percussion. But what we see is with our blended V3, these are the selected microspines, we're still above our red requirements line. So these were some of the other designs that were a bit lower performing and different radius of boulders that we were testing on. Okay, so this is kind of the final wrap up from all of that testing, which was probably about a year. Is that right? I don't know. That was your life for about a year, I think. A year and a half. Yeah. All in one slide. So here we have our kind of requirements where the rocks are probably in the rock suite. Blue is the requirement, yellow is our performance, and so we were feeling pretty good, and we were going to take this data to a gate that we call the preliminary design review, which is a formal NASA life cycle milestone. We also at that point had the full gripper, so we did some ground truth testing by using the full gripper on our single cassette test stand to make sure the data was turning out the same. And then probably the best day of my career when we did this full end-to-end test where we gripped, drilled, anchored, and lifted this boulder off the ground, all while having a simulated microgravity preload on the gripper. All of that happened autonomously, but it's pretty straightforward kind of state machine, and so I didn't want to dive too much into the details here. Probably the worst day of my career was maybe 3 months later or so when this mission got canceled. Unfortunately, NASA is a very political agency, and so the Congress and the White House changed, and like many times before, they decided to go in a different direction. But this is what it would have looked like, pulling that big boulder off the surface. Okay. So deep breath. If you kind of zoned out during all of that detailed gripper talk, you should come back. We're going to talk about bigger robotics stuff now. Climbing robots, where I started this talk, it's more than the gripper, right? It takes more than a good gripper. It takes a good gripper, but it's more than that to climb. So here's the Lemur 2 robot. Here's the Lemur 3 robot. with a perception system on the back here that we'll talk about. We've spent a lot of the last 2 years trying to make that system autonomous. So I want to give it a waypoint somewhere on a cliff face and have it decide for itself where to grip, how to path plan, how to balance the forces, and make it to that endpoint. And so to do that, we need perception system. We need some ability to evaluate what's a good place to grasp, what's a bad place to grasp. With a microspine gripper, right? This is not asking your local rock climbing expert. We need good control. So on a vertical surface, balancing your forces is very important. You can ask your expert rock climbing friend about that. And then we need path planning both at the kind of footstep level as well as the regional level. So let's talk about perception system. We did some trades. We ended up with a LiDAR, in part because it's insensitive to the illumination conditions. So for testing in cave environments, that's nice not to have to bring a giant floodlight with you. We do have a camera on there that collects texture information, but right now all we're using is planning. All we're planning on is the point cloud. I hope in the future that we can kind of take some of that visual imagery and do some prediction in terms of the rock texture, rock strength, rock type off of the imagery data, because right now all we have is the 3D geometry. But we use that because that's what we have, and we stitch together multiple scans, right? So we can create a global map from multiple scans, and we feed that into our graspability server, which is essentially trying to decide, where should I put my next foot. So machine learning is a pretty good approach here. That's what we did. Fairly straightforward neural net. But that's only going to be as good as the data that you feed in, right? And we don't have a lot of good labeled data, and it wasn't really practical to do a bunch of grips, thousands of grips with these microspines across different rock faces. And so kind of did a shortcut where we hand annotated some of these walls with our, in strong air quotes here, our expert opinion on what would be a good place to grip and what would be a bad place to grip. So the result, when you train on these kinds of data sets, maybe 10 of these walls, and then run the output on that same wall as if it's never seen it before, you see good match, which tells you, okay, like your algorithm's working, but it's still only as good as that data. And so I think there is also a lot of room to go here in terms of getting some ground truth or accumulating the data during the climbs. We have 6-axis force torque sensors at each of our wrists, so we collect a lot of that data, but we're not feeding that back in to kind of improve the model as we go. But here's what it looks like in the field. So you can see it's kind of telling us to avoid some holes and ledges in this corner. And that's essentially where to put the center of a gripper. So it's not saying that the robot can't traverse those areas. It's just saying don't put your foot exactly on that corner. When we're in the field, we also collect a bunch of data. We use PhotoScan and other tools, and then feed them into a simulation environment. We use Gazebo, but it sort of doesn't matter. So we can do sort of pseudo field tests in simulation in the lab in preparation for the next time we go out into the field. OK, so here's the end result. This is a mostly autonomous 4.3 meter climb. This is in an uncreatively named park called Granite Mountain. And it's pretty slow. So you can tell because it's kind of a race whether the robot's moving faster or the sun is moving faster. And then a gust of wind came and blew over our camera tripod there. But the good news is, NASA doesn't really care about speed. So at 4.3 meters in the 8 hours we were testing, we would make it from the bottom of the Grand Canyon to the top in about 6 or 7 months. Opportunity rover has been on Mars until very recently alive and roving for 13 or 14 years, right? And Curiosity is at 6 or 7 years now. So these speeds are actually acceptable for NASA, unlike my new job at Amazon, where I will be promptly told to find a new idea if we're moving at this pace. OK. So one of the reasons I really like iterative design, we're going to enter the speed round now, is iterative projects tend to kind of branch out. So you'll be building a new design and you'll get an idea of like, hey, what if we used it for this? So one of the ways that happened with our asteroid grippers was for neutral buoyancy experiments. So if you're in microgravity, it's actually very similar to being underwater in neutral buoyancy. And so here is a, can you guys see this? I hope it's just my angle. This is a 3-meter cube size rover called the Hercules. It's on the Nautilus exploration vessel. This is about 2,000 feet below sea level off the coast of Hawaii. So these big ROVs were trying to drill into the seamounts to do some science on the mineral deposits that were there. But they were having trouble that the currents and the forces of drilling, same as on an asteroid, were kind of causing them to move around, and the drill bit was getting jammed in the hole. And so bring to the rescue a big gripper. And this doesn't have microspines, it just has these big claws, so 16 gigantic, I don't know what kind of fish you catch. These are actually fish hooks, but they're like, they fill up the size of your hand, so it's like a great white shark fish hook. And we were able to anchor to the rock and support these underwater vehicles. I love, the bio-inspired robotics part of me is still kind of jealous that even at 2,000 feet below sea level, nature is just hanging out, laughing in your face about how far you still have to go. So we've also looked at ice climbing. So using a lot of the same software, a lot of the same perception system, just with a new gripper, we're now climbing on icy surfaces. So this is in a cave up on Mount Rainier, a glacial ice cave. It's caused by the volcanic gas actually melting out the underside of the glacier. Here's the robot. It's an inchworm-inspired robot. The quadrupeds are great for stability. We use a rotary gate, so we always have 3 feet in contact. We're pretty stable. When we go to an inchworm gate, though, the benefit is you can take a much larger stride length per step. So with lemur, we move about 30 centimeters for 4 steps and a body shift. With this inchworm style robot, we can move about 80 centimeters per step if we're cartwheeling. And so as long as your gripper can react kind of the arbitrary 6 degrees of freedom wrench, then this is maybe a better solution. Here's how the LiDAR kind of works. It needs a little bit different kind of filtering, but these caves are kind of 7 to 10 meters in diameter, but they can go for kilometers. Really wild environments to be in. And they come with all different kinds of terrain types. So on the top, these are called penitentes. So when the sun kind of melts, you get an instability and you get these basically sharp spikes. So another hard problem, if anyone's looking for a thesis topic, is try and do computer vision and path planning on a field of spikes like these penitentes. Seriously, they're presumed to exist on the surface of Europa, so that might be a problem that we face. Now, with the icy environments, we can't mimic all of the parameters. The geotechnical properties of the ice at 100 Kelvin in a vacuum are not the same at all as what we find on Mount Rainier. And so we actually use a 3-prong approach. We test in the field, in a thermal vac chamber, and in simulation to get things like Enceladus's very low gravity, 3% of Earth. So I'll take us from the cold to the hot. This is my postdoc, Carolyn Parchetta, standing fearlessly next to a lava lake. There's a picture of me like this that I never show because I look absolutely terrified. Here's iterative design again. So we're lowering these robots down into eruptive fissures that occurred in the 60s and 70s. And it's using Xbox Connect in V1 and a structure sensor in V3 to collect geometric data about the fissure, and we feed that into fluid dynamics models of the eruption. So here's what that data looks like. It's not always aligned to gravity. It's not a big rectilinear crack. It sort of follows propagation lines that are weak spots in the rock, and it also has some sinuosity that kind of goes with the kind of fracture mechanics of the basalt and how many layers there are on top of it. Anyways, this was first of its kind data that the science community was really happy to get, and it was with mostly 3D printed and off-the-shelf components. I've also done a lot of work with gecko adhesives. So gecko is my favorite animal by far, nature's most amazing climber. The way they climb is with these hierarchical structures of hairy growths on their feet. So they start at the millimeter scale and they go all the way down to the nanometer scale. They stick using van der Waals forces, which is great for space because it doesn't depend on pressure or temperature. So they work well in space. One of the interesting things about them is that they only work in one direction. So Aristotle noticed that when a gecko climbs head first downwards, it actually flips its feet around to face the other direction. So a fun little thing was I got to cite Aristotle in my PhD thesis, which I was like, that was awesome. And so we built a robot. They let me graduate when we finally got this robot working. This is 2009, so it's a bit old. This is a sticky bot. I worked on the adhesive feed, and then Sang-bae Kim is the designer of the robot. So this is using that gecko-like adhesive, and it only climbs vertically in that one direction because the stickiness is only in that one direction. Let's see, did I miss one? Oh, these are a little bit out of order. That's OK. We also use electrostatics to stick. So this is kind of like a capacitor. You create high charge between these interdigitated electrodes. And on a conductive surface, you'll get a matching field and you'll stick. And on a non-conductive surface, you create dipoles that actually cause you to stick. There's one equation here which tells you that the force you get is proportional to the polarizability of the material and the electric field strength. And so with an equation, this officially is a technical talk now. We also build these small climbing robots that we test not only microspines but also those electrostatics on. So this is some work that Kaylin Carpenter has led. And then we went back onto the zero gravity airplane to test these as well. So this is climbing across common spacecraft materials, so thermal blankets, solar panels, carbon fiber. This would be for things like inspection of the space station or satellites, orbital debris mitigation. I think you'll see in a moment some grippers made out of this material as well, grappling different objects. So space is full of garbage. If you saw the movie Gravity, that's actually not, super made up. The potential harm of a catastrophic accident is real. And in fact, old Soviet satellite crashed into I think it was a DirecTV satellite in 2008 and created 10,000 smaller pieces of debris that are now a big cloud that we actually have to boost the ISS every once in a while, the International Space Station, to make sure that cloud doesn't come and hit the astronauts. Another former CMU student, Simon Kalush, built this inchworm robot for us while he was an intern. And then we flew some of these to the space station. So this is Jeff Williams. I don't know what his alma mater is, but he's testing the gecko adhesives here on the space station and proving that Newton's laws, in fact, hold in space here as he tries to pull off the adhesive gripper from the wall of the space station. He realizes I need equal and opposite. There we go. So this was pretty cool to see our stuff go up to the space station. The ultimate goal is a concept like this, where you'd have a robot that would, be your assistant on the outside of the station, right? And kind of a fun side note: the adhesives have not only applications in space, but a lot of terrestrial applications. So we spun out this gecko material to a startup company, and the founder of that startup company sent me this picture unannounced in my inbox one day, and he said, "Hey, you never guess who was playing with the gripper you gave me." So yeah, I built this one, and this was a couple of years ago, obviously. And so you too can buy a Gecko gripper now if you'd like. They got acquired by a company called OnRobot, and are selling Gecko grippers for pick and place in factory and manufacturing lines. All right, I think I ran a little long, but I hope it was exciting and interesting. And this is my get off the stage slide. Here's our robot. So I actually am inspired by this. We're going to have a lot of work to do for a long time to come. And if you think this isn't good enough, here's in Death Valley, and here's our robot. So, yeah, thanks very much. So time for a few questions, I think. Yeah.
For that climbing robot you showed, why was it so slow to do that?
Yeah, so the lemur robot, why is it so slow? A lot of it has to do with the operator system, essentially. Like we have a lot of checks to make sure, you know, it is acting autonomously, but we sort of confirm quite often as we go. So part of it is that, but part of it is also just the motor control and the speeds at which we can operate those motors. They're in a high torque application, and so the limbs are just kind of slow. Each gripper takes about 20 seconds to engage, to disengage. So it's kind of a combination of things, and it wasn't a priority for us until you get out in the field, and then you're sitting around all day, you know, wondering why you didn't make it faster. Yeah. Other questions? Yeah. Yeah. So the applications are obviously very different, but I think the challenges of grasp and manipulation are somewhat common. So, you know, Amazon has a huge catalog of items that they sell, right? Everything pretty much you can buy on Amazon. And so there's not as much structure in their fulfillment centers as you would get in a plant that's, you know, only producing solar panels, and you have predictable kind of automation path. And so similarly, out in the solar system, you know, the rocks that you come across, the icy surfaces, they're very unstructured. And so, you know, maybe that's a bit of a similarity, but, you know, it's also a bit of a new direction for me. But I think, you know, grippers and grasp, you know, is common across the two of them. Yeah. Yeah.
So what's the weight of each robot? I know you probably don't care about its space. And then how long does the battery run when you have them?
Sure. So the lemur robot there, when it's just the robot, is about, what is it, 29 kilograms. It's pretty heavy. In part, that's because we really wanted to focus on the autonomy and didn't want to rebuild the robot. So it's still got a bunch of PC-104 electronics running the low-level motor control, which are heavy. Now, it's 29 kilograms when it's unloaded. We actually have a bunch of science instruments that we put on there to try and do mock missions. And so we have like a X-ray fluorescence instrument that can give you the atomic abundances of the rock, the elements in the rock. We have a DPV spectrometer. We have a bunch of these kind of science instruments that ride on its back. When we load it up with everything, it's like 52 kilograms. So we have a gravity offload. So we're supporting a lot of the weight of the robot so that we can work on the planning and the perception parts of the problem. Yeah. Let's see, the other ones. On the small side, the little micro climbers weigh under 100 grams. So those are the ones you saw driving in zero gravity. Yeah, the iceworm robot, I think, is about 20 kilograms. So it's still pretty heavy. That's actually using Robosimian joints. So JPL's entry into the DARPA Robotics Challenge was Robosimian. And since those were laying around, there were spare joints, we said, let's use those so we can focus again on the climbing problem and not on building a robot. So ultimately, I think that would be lighter as well, but yeah.
The battery?
Yeah, so lemur has a battery. It can run for about an hour, but typically we just take the battery out and run it off of a power supply. Yeah. The same is true. We didn't even bother to put a battery in the ice climbing robot. We actually think that might be a tethered system. So the moondiver concept I showed you at the beginning, that tether that it repels on, that's not just a rope. That's actually power and communication lines back up to the lander so that the lander can communicate back to Earth. And so we've done a lot of work looking at those kinds of structural and electrical tethers. Yeah. Yeah.
Can you talk a little bit about you talked about 3 different gripping technologies,
Yeah.
spine,
Yeah.
pieces where you think each of them excel?
Sure. Yeah, so spines, claws, right, are really good on rough surfaces or penetrable surfaces that you don't care about after the fact. The Gecko material is much stickier than the electrostatics, you know, on a glass surface about 5 times higher adhesive pressures, but it really only works well on smooth surfaces at this point. So the benefit of the electrostatics is that it'll work not only on smooth surfaces, but on surfaces, you know, that might have some texture, even surfaces that are like semi-rough. The Gecko falls off pretty quickly, so it would stick to something like the surface of the table, but if you got to something like the interior painted wall, the Gecko material starts to not really be effective.
The electroadhesives have other trade-offs too. Is there, do you think, a fair amount of interest in that?
Yeah, so the electroadhesives don't work well on materials that aren't very polarizable, so rocks, mud bricks, these kinds of things, because there was some interest in trying to use them for climbing robots in Iraq or Afghanistan or these kinds of places. It's not actually a good match for that. But on the outside of satellites, you don't find a lot of earthen materials. It actually works quite well. There is, I think, some interest in that. So you've seen not only our work, but SRI really pioneered the use of electroadhesives. Rob Wood at Harvard has done a little bit now also with Matt Spenko at IIT. We've got a microfabrication process that we make our own films for that at this point that are much better than the kind of original publications. So there is a lot of interest, and Harsha started a company, I think, called Grab It or something like that. Yeah, so I think there's some interest. You can shock yourself. Been there. You know, it's about 6 kilovolts, but nanoamps, right? And so you say, oh, but it's no current. It still stings. Yeah. Yeah.
You talked about using simulation. I was wondering what specifically, like, did you try to simulate, and like, what were your experiences?
Yeah, so the simulation has been really good for looking at path planning, for instance, through these kind of complex cave environments. It's been really bad at doing the contact modeling. So trying to understand the, you know, gripper rock interaction, or even, to be honest, the electrostatics or Gecko adhesive performance doesn't seem to be always modeled well. So yeah, so we use it for like workspace analysis to evaluate our path planners, but we tend not to use it in terms of predicting grip strength or stability, that kind of stuff. Yeah, we could probably do more there as well. I think I'll take maybe 1 or 2 more, and then I'll stick around afterwards, but I'll let everybody else go. Yeah.
Sort of an extension to that, you talked about being in a situation where you were, the range of strength of the rocks that you could expect was really varied, and how does the design process get directed in such a situation, like in terms of what type of hooks you experiment with?
Yeah.
Especially when you don't really have a good simulation or that.
Yeah, it means you end up with a lot of testing, right? So we try and envelope the possibilities. So we look for the, you know, potential minimum and potential maximum of that parameter, and try and make sure we're testing beyond both of those. You know, we have to do this for space robotics all the time, because there are a lot of unknowns in those situations, but it drives a lot of testing. So, you know, better simulation tools would speed that up and could potentially save a lot of time and money, but we haven't gone down that path yet. Yeah. All right, so thanks very much for coming, and I'll stick up front. If you have other questions, please just come up and chat, and don't hesitate to get in touch with me if you're interested in the work or interested in a job. Yeah.